how does this higher dimensional theory align with or challenge current scientific models such as quantum mechanics and general relativity? See, it is obvious that both quantum mechanics and general relativity are extraordinarily successful theories. The fact that they are no longer looked at as simple theories, they are seen as two different branches of physics, in itself says that there is something going on which resembles, which aligns with how things are. If they were to be pure speculative, just pure mathematics, not aligning with what's happening in the world, then the inconsistencies would have been too many. As different as they are, the foundational principles of quantum mechanics and general relativity cannot be any more opposed. General relativity assumes space-time to be the fabric of reality. Our three-dimensional world, of course, general relativity calls it four-dimensional, 3 dimensions of space and 1 dimension of time. But if we truly understand dimensions, we will not be calling space-time fabric 4-dimensional. It is 3-dimensional. Time is a component of space. In fact, it's an inseparable component of space. Quantum mechanics, on the other hand, cannot assume space to be the fundamental reality, because it is operating at such scales. It is discovering things that is pointing in a direction where the fundamental nature of reality is not space but some kind of mind. Quantum mechanics talks about superposition. It talks about entanglement. It talks about tunneling. It talks about observer effect. Whereas general relativity is gravity. How mass curves space-time. And space-time in turn governs how a mass has to move within this curved space-time. General relativity has nothing to do with observer effect, has nothing to do with quantum states, has nothing to do with superposition. But they both explain things beautifully on their own scales. Quantum mechanics is very successful in predicting things, especially probabilities. It is a probabilistic theory when compared to the deterministic theory of relativity. This is one of the reasons Einstein did not like quantum mechanics, because it was dealing in probabilities. And entanglement apparently was breaking the fundamental rule of speed of light. Entanglement and collapse of the wave function were happening immediately. Two particles could be entangled at distances so vast that it's impossible for them to communicate with each other instantaneously. But if the state of one particle collapses, the state of another entangled particle immediately collapses. So it's almost like they're communicating instantaneously, faster than the speed of light. And Einstein called this spooky action at a distance. He did not like it. And that is why he said there is something incomplete in quantum mechanics. God doesn't play dice with the universe. Universe is deterministic. There are specific laws and things happen in a certain way. But quantum mechanics has shown again and again and again that it seems like God is playing dice with the universe. There are multiple states in which a particle can exist. And before observing it, you can never know where this particle is. Let's say an electron. In the traditional understanding of an atom, we thought there is a nucleus and there is an electron revolving around the nucleus in different orbitals. When electron jumps from one energy level to another energy level, it releases a photon, particle of light. And these energy levels are definite. It cannot occupy any energy state in between. But now, quantum mechanics has shown beyond any doubt that there is no electron. There is something called as an electron cloud, a probabilistic wave function, where electron itself exists as a wave. And when you observe it, it doesn't pop out as a particle. That is again a wrong description. It's almost like there's a wave, and when you watch it, somewhere this wave rises enough above and holds its position to be able to say that's an electron. But it is still a part of the wave. A three-dimensional ball doesn't pop out. That's our classical definition of elementary particles, that they are particles. Now, what quantum mechanics is showing is that they're not even particles. I mean, this is where we get the wave-particle duality of light. Light behaves both as a wave and as a particle. How is that possible? How can one thing exist as two things in Einstein's world? It's just not possible. But in the quantum world, that is how they are. Before an observer comes in, everything exists in an altogether different state, a state of superposition. It is the observer that collapses the wave function and makes it possible for us to identify and measure something. Without this observer effect, there is really nothing to measure. Everything is in a state of superposition. Now, the challenge has been, how do we reconcile these two theories? That has been the search. Is there a grand unifying theory that can unify quantum mechanics and gravity? And we've been calling that theory quantum gravity. Again, assuming that if only we can get this mathematical equation that expresses gravity as a quantum phenomenon, then we can explain the large-scale structure of the universe. But the problem is, gravity does not follow quantum rules. Because Einstein was right. Gravity is not a force. It is not something that is attracting things. It is a distortion in the space-time fabric itself. The effects of gravity is not limited to the object. Time slows down around heavier objects. Light bends around heavier objects. And we know that around a black hole, time even stops. I mean, inside a black hole, time stops and there is no space. Space is curled up so much that you cannot even recognize it as space. Now, how do we understand this? On the one hand, quantum mechanics says all the values are quantized. Energy is released in discrete quantities, discrete amounts. Now, here, general relativity says space-time is a smooth fabric. According to the equations, when there is no mass distorting this fabric, it is absolutely flat and it is smooth. But if you apply these equations at the quantum level, it leads to all kinds of errors, leading to all kinds of infinities that cannot be reconciled. So, we've been trying to quantize gravity to show that space-time fabric is not smooth, but it follows the quantum rules. But the problem is, at the scales at which quantum mechanics operates, gravity is so hard to detect. Gravity is one of the weakest forces. I mean, there's an example that's given famously. I mean, you take a comb and rub it to your hair, and if there are a few pieces of paper, small pieces of paper, if you keep the comb on top, it attracts the paper. That's electromagnetic force. Now just imagine the entire gravitational force of the earth is acting on that paper to keep it down. And the static force between that paper and a comb can lift it up. That is how weak gravity is. But it's a long-range force. It governs things on the large scale. It is weak, but its range is, in fact, we don't even see gravity as something that can have a value of 0. Now, how do we reconcile these two theories? Both are explaining something very important. Quantum mechanics is saying that the fundamental nature of reality is something other than space. General relativity is saying there is still order here. It is not all probabilistic. We all are experiencing our universe in an objective way. Each individual is not projecting their own reality. Just imagine if that was the case. If each individual was creating their own realities, then there would be no common experience. We could not have agreed on anything. This is the problem. If you simply accept quantum mechanics and just say, well, it is the observer effect, depending on where you are, depending on who's observing the universe, it is what it is. It doesn't align with the smoothness of things. It doesn't align with the laws that are very precise. Bring in consciousness. It beautifully aligns these two theories. It ties them up in a way that after understanding how consciousness affects the nature of reality, how it operates on the smallest of scales and on the largest of scales, we'll see that these two theories are not two theories at all. They have always been describing one fundamental reality in slightly different ways. If consciousness is the ocean within which everything is moving, if consciousness is the governing principle of the entirety of what we recognize as our visible universe, then general relativity simply ignored this ocean. It was not necessary. It was looking at such large scales, there was no need to look in between. You could simply study two objects and you could assume a space time fabric and do the calculations. There was no necessity to acknowledge this ocean. But at the quantum level, you cannot ignore this. Of course, you don't see it as an ocean, but it is recognized as an observer effect. What is observer effect if not for the effect of consciousness? Again, it's not human individual consciousness. It is consciousness which is the very foundation of existence.